Welcome to another deep dive, everyone. Today, we're taking a close look at a chapter from the Class 12 Physics textbook.
Oh, interesting. Which one?
It's the one titled Magnetism and Matter, published by India's National Council of Educational Research and Training.
Ah, NCERT. Great choice.
Definitely. Huge thanks to them for making this resource so widely available. So, we're going to approach this imagining we're back in school, maybe 15 years old.
Right back to those physics classes.
Exactly. And this chapter, magnetism and matter, might sound a bit daunting at first, but honestly, it's packed with these really cool concepts. I mean, we're talking about why compasses point north.
Always a classic mystery.
Yeah. And what about those invisible forces that make magnets, attract or repel?
The magic of magnetism. And let's not forget the big question, are there magnetic monopoles out there?
So many fascinating things to unravel. And, magnetism, it's not just some theoretical idea. It's all around us, literally everywhere.
Absolutely. Think about it, the Earth's magnetic field. It's like a giant shield protecting us from all that harmful radiation coming from space.
Oh, yeah. And even closer to home, just look at your refrigerator. Those little magnets holding up your photos and notes, it's magnetism in action.
It's true. Humans have been intrigued by magnets for centuries. Way back in 600 BC, the ancient Greeks discovered these naturally magnetic stones.
Really? That long ago?
Yeah, they called them magnets after the region of Magnesia where they were found.
Makes sense. But they couldn't have known back then how these things actually worked.
No, the real breakthrough came much later, in the 19th century. That's when scientists discovered the link between electricity and magnetism.
So wait, are you saying electricity and magnetism are somehow connected?
They're fundamentally intertwined. It turns out that whenever you have moving electric charges, they create magnetic fields.
Wow, so every time electricity flows, there's magnetism involved.
You got it.
Yeah.
That's the key to understanding how magnets work at their core. Let's take the classic example, the bar magnet.
Oh yeah, the good old bar magnet with its north and south poles. But what's really going on there?
Well, remember that experiment you probably did in school with the iron filings?
Yeah, you sprinkle them around the magnet and they form these cool patterns.
Exactly. Those iron filings, they act like tiny compasses, aligning themselves along the invisible magnetic field lines around the bar magnet.
So the patterns they form are like a visual map of the magnetic field.
Precisely. You can see both the direction and the strength of the field. The closer those lines are together, the stronger the magnetic force.
So it's like a blueprint of the magnet's power,
Yeah.
all thanks to those iron filings.
It's a great way to visualize something that's normally invisible. Now, here's where things get even more interesting. A bar magnet behaves very similarly to another object, a solenoid.
A solenoid. Now, what's that again?
It's pretty simple, just a coil of wire with an electric current flowing through it.
Oh, right. And you're saying this solenoid creates a magnetic field, too.
Yeah, and it's strikingly similar to the field of a bar magnet. It really reinforces the idea that moving charges are at the heart of magnetism.
So whether it's electrons flowing in a wire or the electrons spinning within atoms, it's the movement that creates the magnetic field.
It's a beautiful example of how seemingly different phenomena can be connected by fundamental principles. But let's zoom in even further now. Imagine you take a tiny compass needle, which is like a mini bar magnet,
Okay, got it.
and you place it inside a uniform magnetic field.
Like holding a compass near a larger magnet.
Exactly. What happens is the compass needle experiences a torque, a twisting force, that tries to align it with those magnetic field lines.
Ah, that's why a compass always points north. It's aligning itself with the Earth's magnetic
It
field.
is. That's it. And there's another principle at play here. The compass is trying to find its lowest energy state.
Lowest energy state, meaning
It's like when you roll a ball down a hill. It naturally wants to reach the bottom, where it has the least potential energy.
so the compass is like, I just want to chill out and be aligned.
Something like that. Now, there's one concept that often trips people up. Have you heard of Gauss's law for magnetism?
I have. It's a bit of a head scratcher.
It is, but it's super important. It states that the net magnetic flux, which is like the total number of magnetic field lines passing through any closed surface,
Okay.
it's always zero.
Zero. Always.
Always. Imagine you have a magnet and you completely enclose it in a bubble, any kind of bubble. The number of field lines going into that bubble will always equal the number coming out.
So it's like a perfectly balanced system no matter what. But what does that tell us about the magnet itself?
Well, this is where the mystery of magnetic monopoles comes in. Unlike electric charge, which has positive and negative like protons and
Yeah,
electrons.
right.
We've never found a magnetic charge existing all by itself.
Meaning there's no such thing as a lone North Pole or a South Pole just floating around.
Exactly. They always come in pairs. That's what Gauss's law suggests. We've looked and looked, but no magnetic monopoles yet. It's one of the biggest puzzles in physics.
It makes you wonder, what would the world be like if we did find one?
It would be a game changer, that's for sure. But for now, the search continues. Now that we've laid the groundwork with magnetic fields and these mysterious monopoles,
Right.
let's move on and see how different materials react when they encounter these invisible magnetic forces.
Okay, so we've explored these magnetic fields and these hypothetical monopoles. But how do different materials actually behave when they're around a magnet?
That's where it gets really interesting. Different materials respond in totally different ways. Some are attracted, others are repelled, and some just kind of shrug it off.
So it's like materials have their own personalities when it comes to magnets.
Exactly. And scientists have categorized these personalities into three main types.
Hit me with those categories.
We've got diamagnetism, paramagnetism, and the star of the show, ferromagnetism.
All right, let's break those down one by one. What's up with diamagnetism?
Diamagnetic materials are kind of like the loners of the magnetic world. They're actually weakly repelled by magnetic fields.
Repelled. So they push away from magnets.
In a subtle way, yeah. It's like a tiny bit of magnetic resistance. Think of water or copper. They're diamagnetic. They're not going to suddenly jump onto your fridge magnet.
Right, they're just not interested. Okay, so if diamagnetic materials are the loners, what about paramagnetic materials?
Paramagnetic materials are a bit more social. They're weakly attracted to magnetic fields, but it's not a super strong attraction.
So they're kind of like, yeah, magnets, whatever.
Pretty much. This weak attraction happens because the atoms in these materials have these tiny little magnetic moments that try to align with the external field.
So they're making an effort, but it's half-hearted.
Exactly. Aluminum and oxygen are good examples of paramagnetic materials. They're influenced, but not dramatically. And then we have the rock stars, the ferromagnetic materials.
These are the ones that really love magnets, right?
Absolutely. They're strongly attracted to magnetic fields and can even become permanent magnets themselves. The classic examples are iron, nickel, and cobalt.
Ah, the heavy hitters.
Yeah.
What makes them so different?
It all comes down to their internal structure. Inside ferromagnetic materials, you have these tiny regions called domains. Think of them like little neighborhoods.
Okay, I'm picturing it.
And within each domain, all the atomic magnets are pointing in the same direction, like a well-organized community.
So it's not just individual atoms being magnetic, it's whole groups of them acting together.
You got it. And when you apply an external magnetic field, these domains can actually grow and align with the field, which makes the magnetism even stronger.
So it's like those little neighborhoods start merging and expanding their magnetic influence.
That's a great way to put it. This organized structure is what gives ferromagnetic materials their incredible magnetic powers. But here's a question for you. Do you think these magnetic properties are always constant?
Good question. I guess I always assumed they were kind of fixed.
Well, it turns out that temperature can actually play a big role in how a material behaves magnetically. For example, if you heat a ferromagnetic material enough, it can lose its strong magnetic properties and become paramagnetic.
Wait, so you can weaken a magnet by heating it up?
Precisely. The heat basically disrupts those organized domains we talked about. The atoms start vibrating more frantically because of the thermal energy, and that messes up their neat little alignment.
So the magnet's inner structure gets all chaotic.
Exactly. And as the domains become more disordered, the ferromagnetic properties fade away. It's like those organized neighborhoods fall apart and everyone goes their separate ways.
Fascinating. So even something as simple as temperature can have a huge impact on magnetism.
Oh.
So we've got these different types of materials all reacting to magnetic fields in their own unique ways.
Yeah.
But where does this all fit into the bigger picture? Like on a planetary scale even.
Well, let's take the Earth itself as an example. You know how we said the Earth acts like a giant bar magnet?
Yeah, I remember that. But how does that actually work? It's not like there's a giant bar magnet buried in the Earth's core, right?
Not quite, but it's a pretty good analogy. You see, deep within the Earth's core, there's all this molten iron. And as that molten iron moves around, it actually generates electric currents.
Hold on. Molten iron moving around can create electricity.
It can. And remember, whenever you have moving electric charges, you get molten.
Magnetic fields,
Oh,
right? Because of that connection we talked about earlier.
exactly. So all that molten iron swirling around in the Earth's core is creating these huge magnetic fields that extend way out into space. We call this the Earth's magnetosphere.
So basically, the Earth is like one massive planetary-sized solenoid.
You could say that. And it's a good thing, too, because this magnetic field acts as a shield, protecting us from all that harmful radiation coming from the sun and outer space.
Wow, so it's like an invisible force field protecting all life on Earth.
That's a great way to put it. Without the magnetosphere, things would be pretty rough down here. And it's not just the Earth. Magnetism plays a crucial role throughout the entire universe.
Really? Like how?
Well, for starters, it influences the behavior of stars, shapes entire galaxies, and even affects how matter interacts on a cosmic scale. It's one of the fundamental forces that governs the cosmos.
It's mind-blowing to think about. Something we might take for granted, like a magnet sticking to our fridge, is connected to these incredible forces at play across the universe.
It really puts things into perspective, doesn't it? It shows you how interconnected everything is, and it all boils down to these basic principles of magnetism that we've been discussing.
Well, I think it's safe to say that we've successfully navigated this chapter on magnetism and matter. We've covered ancient Greek discoveries, those mysterious magnetic monopoles, and even touched on the Earth's giant magnetic field. We've really come a long way.
We have, and I hope our listeners have gained a deeper appreciation for the power and the mystery of magnetism. It's truly a fascinating subject.
Absolutely. And as we wrap up this deep dive, I want to leave everyone with one final thought. Remember those iron filings, how they arranged themselves along the invisible magnetic field lines?
Yeah.
It's a powerful reminder that there's so much more to the world than what we can see with our own eyes. There are unseen forces at play everywhere, shaping our reality in amazing ways. So keep exploring, keep questioning, and never stop being curious about the world around you.